since that exam, we started doing applied optimization problems. Those are the word problems. Quite often they were geometric in nature. You know, you got some fencing. One example we did was you had like 100 feet of fencing, and you're going to make a rectangle up against a wall. What's the maximum area that can be enclosed? And what are the dimensions of the rectangle that will give you that maximum area? So you have to draw a picture, label the sides X and Y. The area is X times Y, but then to actually do that maximization, you need to use the constraint to figure out how the area just depends on X. Remember doing that? And it's the amount of fencing that's the constraint here. If you got 100 total feet, then X plus Y plus another X has to equal 100. 2X plus Y has to equal 100. You can solve that for Y. Y would be 100 minus 2X. And that can be plugged into the function to give you a function of just one variable. We can avoid multi-variable calculus. That's good. Other problems included, you can maximize a volume when you know the surface area. You can minimize a surface area when you know the volume. That was a problem we did in class. Got a can, cylinder shape. It's got a certain volume. What's the minimum surface area for that given volume? And what are the dimensions, the radius at the top of the can and the height of the can? There was a geometric problem where we tried to minimize, I think it was X plus 2Y, where you travel this distance X, and then you go up at a diagonal direction Y from one point to another. Choose X so that it was like X plus 2Y was minimized. We did the project where it was an economics problem, you might say, a business problem, where we were trying to minimize cost. So we needed a formula for the cost. And the constraints were, well, one constraint was how much paper was used every week. We had a function actually of 3 variables there that we tried to reduce to a function of just 1. In the homework, you had at least 1 or 2 problems like that, and they were a little simpler. That's mostly the kinds of examples we considered. There are other kinds of examples, but those were the main kinds that we considered. We also talked about families of functions. One example we considered in class was the family f of x equals x minus a square root of x. I called this f sub a, but the book doesn't do that. The point is to emphasize that really what I have here is infinitely many functions. One function for each value of a. A was greater than 0 here. And even though I don't know what a is, I can still figure out how the critical point depends on a. And whether it's still a maximum or a minimum, no matter what a is. I think for this example, we got always that it was a minimum. But that minimum sort of moved down the line y equals negative x as a increased. Should be in your notes. We did it maybe about 3 or 4 weeks ago. Just one example. The normal curve family with an arbitrary mu and an arbitrary sigma is another example. I think we did talk about that a little bit in class. It's also in the reading. Don't remember offhand what other examples we considered. But the point is, you should be able to deal with this kind of thing. You should be able to figure out, let's do it quick. You know, what is the critical point of this in terms of a? If I take its derivative with respect to x, treating a as a constant, there's what I get for the derivative, which simplifies to this. I still set that equal to 0 and solve for x. And what you would end up getting is 2 square root of x equals a. I did a couple steps there in my head. And so 4x equals a squared, and x is a squared over 4 if I've not made a mistake. And you could use the first or second derivative test to verify that it gives you a minimum. You can also plug this into the original function to find the actual minimum value. F sub a of a squared over 4. Plugging it back up in here is a squared over 4 minus a times the square root of a squared over 4. A squared over 4 minus a squared over 2, which is a squared minus 2a squared over 4, negative a squared over 4. Yeah. I'm reconfirming what we found. The x coordinate of the critical point is this. The y coordinate is that. That'll be on the line with a slope of -1 through the origin. And as a increases, it moves away from the origin. So you can imagine graphs that are changing as a changes. They all tend to have this kind of shape. And this line is where the minimum is. That's the line y equals x. It goes to the lowest point in the graph. Being able to handle that kind of thing, probably for a different example, could come up on the exam. We also talked about related rates. We've got a number of quantities that are changing. In class, we talked about shrinking pyramids and growing squares. On your homework, you had some other problems. Common kind of example is maybe you imagine, I mean, this is an environmental catastrophe, but you imagine like an oil spill. There's a tanker right there. And you imagine the oil spill radiating out away from the tanker. And maybe you know how fast the radius of the spill is increasing at a certain moment in time. You're interested in knowing how fast the area of the spill is increasing. The area is pi r squared with respect to time. So you always, in related rates problems, you always differentiate with respect to time. A and R are quantities that are changing over time. They're functions of time in the problem. And you imagine that they're nice functions of time that can be differentiated. And so you would say dA dt equals the derivative of this with respect to t. But then just like with implicit differentiation, you have to, in this case, when you differentiate with respect to t, you have to use the chain rule because r is a function of t. You would get 2 pi r times dr dt. That's the chain rule right there. And this would be then an equation that would relate these rates. These are two different rates that are related to each other. Remember, in these problems, you only plug in numbers at the very end. You're always pretending things depend on t, differentiate, only plug in numbers at the very end. Maybe you know dr dt and you know r, you can use this equation to find dA dt. Maybe you know dA dt and r, you can use the equation to find dr dt. Quite often these problems have some geometry to them, like the area of a circle, or maybe the volume of a cylinder, or the volume of a cone. You need to know those formulas. Should remember the one for the circle. If you need one for a cone, I'd probably give it to you. Just to remind you, it's, you know, the volume would be 1/3 pi r squared h. With the volume of a cone shape. We also talked about L'Hopital's rule as another application of derivatives. You only apply L'Hopital's rule to indeterminate forms. So you first have to check, is my limit problem an indeterminate form or not? If it's not, then don't use L'Hopital's rule because it'll give you the wrong answer. If your function is continuous, at whatever you're letting x approach, you just plug that number into the function, get an answer, done. Don't apply L'Hopital's rule. It will give you the wrong answer. You've got to check, is it 0 over 0? Is it infinity over infinity? When I write that, that doesn't mean I can divide by 0. It just is notation, meaning that I've got a fraction where both the top and the bottom are going to 0 as x approaches 5 or something. It doesn't mean I actually plug in 5 to get a 0 on the bottom. I don't actually do that. What you do, you have to take, if it's a fraction, you have to take the derivative of the top and the bottom individually and make a new fraction. It's not the quotient rule. Try to take the limit of that new fraction. Maybe it'll be easy, maybe it won't be. Maybe I'll have to apply L'Hopital's rule again. Infinity over infinity is handled the same kind of way. If it's a 0 times infinity situation, like for example, e to the negative x times x, as x goes to infinity, this is going to 0 and this is going to infinity. You need to convert that to a fraction before trying to use L'Hopital's rule. And in this case, you'd convert it to the fraction x over e to the x, because e to the negative x is the same as 1 over e to the positive x. Sometimes you might have a situation like it's maybe 0 to the 0 power, or maybe 1 to the infinity power. Those are indeterminate forms as well. Before you can use L'Hopital's rule, that's the kind of problems where you need to use a logarithm first. Take the log of both sides. And then ultimately use some tricks to write it as a fraction before you take the limit. We did examples like that. It's a bit tricky, but can be done. Parametric equations and curves was another topic. Being able to graph a parametric equation, a system of parametric equations to get a parametric curve. Being able to take a curve like the line between 2 points or a circle centered somewhere with a certain radius and parameterize it. It's another skill. There are actually infinitely many answers, though if your answer is supposed to model a certain motion, there'd be only one answer. Maybe you're trying to model constant speed motion. That would be the simplest kind of thing. There are various things we did with these things. Sometimes we eliminated the parameter, the t, to get an xy equation for the curve. Sometimes we were content to just graph it. Sometimes we thought about vectors and drew those, at least in Mathematica. Position vector, velocity vector, acceleration vector. The speed was the length of the velocity vector. And then ultimately, the main kind of thing we tried to emphasize was that if you integrate the speed, you get the distance traveled. The speed is the length of the velocity vector. You take the square root of the f prime of t squared plus g prime of t squared. It's the Pythagorean theorem applied to the velocity vector as an arrow that you can draw in a picture. Sometimes that distance traveled function is, you can find it, like if the speed is constant. We even did one non-constant example. That was the example x was equal to t, y was equal to t to the 3/2. We were able to integrate the speed to find the distance traveled. It was a little tricky, but it should be in your notes. We did it about a week ago. Okay, trying to apply the physics and motivate integration. Integrals. Essentially, we've done sections 5.1, 5.2, 5.3, 5.4. We also did a little bit of 6.1 and 6.2. We actually did 6.2 earlier in the semester. That's just pure indefinite integrals like this. We did that back when we were working through chapter 3. It was on exam 2. This was about relating integrals to motion. The integral of the speed gives you the distance traveled. The integral of the velocity gives you the displacement, change in position. This is about thinking about integrals as limits of Riemann sums. This is about the fundamental theorem of calculus to compute integrals. This is about those properties we talked about last Friday, the abstract properties. Didn't spend a ton of time on that in class, but you had some homework on it. You should be able to do those kind of problems. Average value today was in there as well. This section was about graphically constructing antiderivatives as areas under curves, signed areas. That was, we did talk about that in class with this example. The piecewise linear function, and we were thinking about creating a function capital X, f of x, by doing the integral from 2 to x of little f of u du, I think we called it. This was a 3 here, this was a 5, this was a 2. And by thinking about areas, we realized we could find a formula for this no matter what x was. We effectively, geometrically or graphically constructed an antiderivative. We saw that this function ultimately had a derivative equal to this function. Capital F prime of x equals little f, not of u, but of x. You got to be consistent with those variables. This variable has to match this one, and this variable has to match this one. The u doesn't matter. You can call that anything you want. Just don't call it f or x or d. U, v, w, t, doesn't matter. Conceptually, though, you want to emphasize the variable for this function's up here. And when you differentiate it with respect to x, you got to get something that depends on x, not u. A common mistake here is people write a u over there because there's a u there. Variable names don't matter really, but you do want to be consistent about them. I could also say capital F prime of t is little f of t. I mean, it doesn't matter what I call the variable as long as it's consistent on both sides. And I can call it t here even though there's no t up there. Right? The function, did I emphasize this at the beginning of the semester? The function f of x equals x squared is the same as the function treble clef of sharp equals sharp squared. Right? It's just symbols. Those are both the same function because they represent the squaring function. Give me a number as input, square it to get the output. Both of those mean the exact same thing. They are the exact same function, just different symbols. The form of the symbols is irrelevant, though we do tend to fall into habits. And we always use treble clef for function names. Well, that, I mean, yes, it's pretty, but it's, you know, people have a hard time making treble clefs. So that's a pretty quick summary of the things we've talked about since the last exam. You know, there's lots of details, problem-solving details. As I emphasized last Friday, it is important in math to understand both big picture and get good at problem solving. In class, we can talk about the big picture pretty easily. It's hard to do a ton of examples. I mean, I try to do as many as I can fit in, sometimes while I'm talking about a concept, because it's helpful. But you got to put that into practice. That's the purpose of working on homework. Purpose of homework is not to be busy work, even though it feels that way sometimes. The purpose of the homework is to reinforce the bigger ideas that you were supposed to be learning. But just because you kind of get it in class doesn't mean you're going to be able to apply it on the homework. Most of you have experienced that. I've experienced that. I've had classes, math classes in my past where I sort of understood what was going on in class, but then when I got to my homework, I'm like, I don't know what to do, right? I've experienced that too. Or maybe you figure it out on your homework, but then you forget it for the test, right? I've experienced that too. So you just got to keep plugging away is the main theme there. All right, we'll start the exam as usual, 5 minutes early, 12:25.